Now, the last thing I'm going to look at in this video is an identity which they can ask, okay, which is linked with complex numbers. Now, this is quite a specific thing as well. Doesn't get asked an awful lot. It has come up in a couple of mock papers in complex numbers questions. So binomial expansion, we'd usually link in with algebra quite a bit, but these questions came up within complex numbers questions. So I'm talking about questions like this and also like this. So these questions are going to require a bit of a base knowledge of complex numbers, okay? So I'm assuming a bit of complex numbers knowledge as I go through these. So they look like very different questions in how they're phrased. Use the Morris theorem to prove, and then they both say completely different things, but they can both be proved in pretty much the same way. So there is a trick to this. If you haven't seen this before, it would be nearly impossible to do out and just by trying it out for the first time. To be honest, you kind of nearly need to know the starting point to know where to go with this. So the starting point is to start with the following. Cos theta plus cos theta plus I sine theta to the power of 3. Now this is the same for actually both of these, two completely separate exam questions, but they'll both start with this. So if you didn't know that was your starting point, you'd be off to a bad start. You probably wouldn't know where to go with this at all. Now, I'll show why this is our starting point right now. So using de Moivre's theorem, okay, we can say that this is equal to cos. So there's no modulus at the front, so it's just cos, and then you'd multiply the 3 by the theta. So cos 3 theta plus I sine 3 theta. So as I said, a bit of knowledge of complex numbers needed for this. So cos theta plus I sine theta cubed is equal to this, okay? Now, that at least has the sine 3 theta, or the cos 3 theta in it. So we can see a little bit more linking into the question. But we need to remember that this is our initial step if this was to come up in a question. So the next step then is to find this cos theta plus I sine theta all cubed in a different way. So where am I going with this in terms of binomial expansion? Well, this is where the binomial expansion actually comes in. So if you were to cube this out using your binomial expansion theorem, now I'm going to use Pascal's triangle for this one because cubed isn't that far up. So let's just have a look. So cubed is going to be this one here, because you'd have x plus y to the 1, then squared, and then this one will be cubed. So actually, so we'll take it down here, that this would be equal to, and now binomial expansion theorem says it's the first term to the power, so cos cubed theta, plus then I'm going to use my Pascal's triangle down here to put in a 3, and then you would have that first term with the power dropped by 1 multiplied by the second term, which is I sine theta. Now I'm going to go down the line for the next one. You'd have another 3 in front of this next term, and what you'd have is your cos theta would only have a single power now, but your I sine theta is going to have a power of 2. And then lastly, it's going to be plus 1. We don't need to really put in the 1. Plus I sine theta. And then that's going to be to the power of 3. Okay, so it's quite a unique question. It looks a little bit messy, but let's keep going with it. So we need to tidy up this now. How will we do that? So the way I'm going to do it is I'm going to actually just square out this and cube out this. So I'm going to write this out as a long line here. So you have cos cubed theta plus, and then the second one is going to be, I'm going to actually put the I at the front. You'll see why in a minute. 3 cos squared theta sine theta. Then we have plus. Now, this is where we used to have another bit of knowledge of complex numbers. When you square this bracket, you must square the I. Okay. Now we should know that I squared is -1. So 3 cos theta. I squared is -1. And then sine squared theta. And then the last one is going to be I cubed sine cubed theta. Now, what's I cubed equal to? Let's just write it down for a second. So I cubed is the same as I squared times I. We know I squared is -1. So that's equal to minus I. Okay. So minus I is what we would get when we cube out I. So that means, as I said, it's quite a long one. We'll have cos cubed theta, it's our first term. We'll have I times 3 cos squared theta sine theta. It's our second one. Now we'll have -3. I'm just putting this minus with the 3 here. And then you have cos theta and sine squared theta. Now, the last term we then have is, so that's the same as minus I, so it's minus I times sine cubed theta. Now, where on earth have I gone with this? So, we're saying that this, let me just scroll back up a little bit for a second, sorry. So, that is the same as this up here. Okay? We're saying that that is equal to this. But it's also equal to this up here on the top right in a much simpler way. But if they're both equal to cos theta plus I sine theta all cubed, okay, so this is equal to cos 3 theta plus I sine 3 theta. Now, why is that good? Well, if I quickly come back up to the original questions in each of them, it's proved that cos 3 theta equals, or proved that sine 3 theta equals. So we can combine the two of these. Again, a little bit of knowledge of complex numbers needed, in that what we can do with equality of two complex numbers is you can set the real parts equal to each other, or set the imaginary parts equal to each other. So the real parts are the parts without any I, so cos 3 theta, and here we have cos cubed theta has no I, and also this over here has no I. So we can then say that, so up to this point it would be the same for both questions. But now let's say if it was the cos 3 theta one, we would just go with the following. We would say cos 3 theta is equal to cos cubed theta minus 3 cos theta sine squared theta. Now, I might need to check what exact form they want it in. Cos 3 theta equals 4 cos cubed theta minus 3 cos theta. Okay, so unfortunately, there are a couple more, one more trick involved in this now. So it's quite a tricky question, but the only good thing about it is if it came up, you'd hopefully have seen it before. Now, in my final answer, there are no sine thetas, okay? It's all cos thetas and cos 3 thetas, so these are all good, okay? So that's good, that's good, that's good. This, however, is not good. So again, to be honest, to spot this will be quite tricky, but the fact that you may have seen it before is what's going to help us. So what we'll do with this is, we will have to replace sine squared theta. So the way we'll do that is we need to use the following formula. Which is in our log tables. Okay. And we need to rearrange that to say that sine squared theta equals 1 minus cos squared theta. Now, why would we do that? The reason we'll do that is we can now replace the sine squared theta with something to do with cos squared theta. So we can say cos 3 theta is equal to cos cubed theta minus 3 cos theta times 1 minus cos squared theta. Okay, so nearly there. So we then have cos cubed theta minus, and if I multiply these out, 3 cos theta times 1 is just 3 cos theta. 3 cos theta minus 3 cos theta times minus cos squared theta is equal to, we minus by minus is a plus, 3 cos, and that'll be cubed theta. So then we have a cos cubed theta, so it's 4 cos cubed theta minus 3 cos theta. Okay, so let's go back up to the question, make sure that's what they wanted. 4 cos cubed theta minus 3 cos theta. Okay, so that's good. So that will be this one done. Now for this other one over here, so obviously these are two separate questions, so you don't have to do both of these in the one. For this one on the left, for sine 3 theta, so as I said, it would be the exact same steps down to this point here, okay, which you wouldn't take the next few steps. What you do instead is you would take the imaginary parts and let them equal to each other. So you'd have your sine 3 theta, that's connected to an I, so that has to equal the parts that are connected to an I up here, which are this and this. So we'll actually just go over the side to do these then. So we can say that sine 3 theta, that's our imaginary part down here, equals the imaginary parts up there. So 3 cos squared, this one up here, 3 cos squared theta sine theta. And then the other imaginary part is, careful, I have to take into account that minus actually, is minus sine cubed theta. And I do want to check the phrasing of the question again. They want this with only sine thetas in the answer. So it will be very similar to the other one. If you only want sine thetas, you're going to need to get rid of the cos squared theta. Apologies. So if we only want sine thetas, we want to get rid of the cos squared theta. So we will use that same thing again, that cos squared theta plus sine squared theta equals 1. So therefore, cos squared theta equals 1 minus sine squared theta. So just using the other way around this time. And then we replace this cos squared theta with 1 minus sine squared theta. So sine 3 theta equals 3 times 1 minus sine squared theta times sine theta minus sine cubed theta. Let's put this all together. So that will be equal to, so sine theta times 1 is just sine theta. So you have 3 times that, so 3 sine theta. And then sine squared theta by sine theta is sine cubed theta. So it will be minus 3 sine cubed theta. And then minus another sine cubed theta. So this is equal to 3 sine theta minus 4 sine cubed theta. Let's go back up and check if that's correct. 3 sine theta minus 4 sine cubed theta, which is correct over this. Okay, so only a small bit of binomial expansion in that, okay, at the start. So that identity is quite unique, quite specific, and does not get asked an awful lot, but it is something that if it came up, the reason you'd expect to know is because you would have expected to have seen it before. If you hadn't seen it before, that would be a fairly tricky question. Even haven't seen it before, it's still tricky, but as I said, the fact you've seen it is what's kind of going to help us with that. So that's a look over our binomial expansion and also then proofs of them couple of identities to do with complex numbers and they also involve a small bit of binomial expansion in them as well. Hope that helped.